Hi, this is Grover with Blue Collar Codes, the Quick and Dirty, episode 20. Going to give you a way to do a simple timing mechanism for your functions. Considering that in the last episode 19, we went over a high level explanation of big O notation and time complexity. Now I'm going to give you a way to time your functions. If you wish to follow along, you can find episode 20.py in the GitHub repository, which is linked in the video summary. So first and foremost, you're going to want to import a function from the time module, and perf counter is something that returns a timestamp from your local machine's clock. And so I'm just going to show that to you right now and what it does, so you can get an idea of what this decorator function here is trying to accomplish. So from time, from time, import perf counter as pf, and then I'm going to, I got to go to Python first. From time, import perf counter as pf. Now I can just do pf, and then as you can see, it's giving me the local machine's clock timestamp. And so the way that you're timing your functions, because it has such a high level of resolution here, you're able to capture the time differentials between something that runs in, nanoseconds or what have you. And so when you're going to run any of your functions and you want to see how much time it takes, you can simply make a timestamp notation before you run your function and then make a timestamp at the end of your function, subtract them, and you have how much time passed while your function was running. And so what I'm going to do here is go over a bit of the examples that I have and just show you the difference between some of the big O notations in that, you have linear, merge sort, and quadratic and cubic function here, and just see what the different times it takes to complete those functions. So here, not to dive too deep into how my decorator function works, but in layman's terms, it's basically a way for you to have this function's code run while you're calling a different function by using this notation. And essentially what I'm doing is, for when I'm calling this function now, because it has this at my timer, it's going to pass my function when I call it separately into this function, record the time, and give this output. So what we're seeing here, based on these function calls down here where I have these prints and so forth, for the first one that we're going over, it's just called my function, and it's just making a summation of a range of numbers based on your input. So if it's 10, it's going to count from 1 to 10 and then return that sum. For this example, I input 1 million as the value of n. And so here you can see it took 0.015 seconds. Now if I were to change this to 1,000, since it's running linearly, it has linear time complexity. Let me save it and run it again. Clear, and then run. You can see that it took a lot less time to run now that the input was 1,000. And let's return it back to, let's say, 10 million. 1 million, 10 million. If I can see all those zeros correctly with my poor eyesight. And so now it took 0.158 seconds instead of 0.000154. So that's the difference based on input and with a linear time complexity. Another linear time complexity would be my reverse it function, that's basically taking an input list and then just recreating a list and reversing it. So as you can see, since the input size and the iterations are only the length of this index, or the last length of the index of the length of the list, the input would be 19 or 20, and so it only goes through 20 iterations versus for this one it was 1,000 iterations versus 1,000,000 or 10 million iterations. So they're not necessarily comparing apples to apples, right? So all we're having here is a summation, and then for this one we're recreating a list. So there might be a small difference based on recreating and using append versus just adding values to an existing value for each iteration. So those are things that there's a kind of a gray area where you can't 100% compare apples to apples when you're comparing these functions, but in the very least, when you alter code within your function and you want to try to increase its efficiency, you can do that by using this perf counter. And the last thing I wanted to show you, and I'm going to end before it completes, is I'm going to change this cubic function to 1,000 as well, because both these functions, the quadratic and the cubic, are the same format, just making a summation, except you have one that is for every value of I, it's going to add all of the values of j for the entire range. And then for the cubic one, it's going to be for all values of I, it's going to add all of the values of j and all of the values of k to j. So for every j, it's going to add all the values of k, and then for every I, it's going to add all the values of j and subsequently k. And so you can see with this time complexity, now that I'm going to make the input size the same, how much longer it will take, because what's going to happen is it's going to hang on the cubic function before it processes, and that's where I'm going to end the video. So let me type over here and go clear, and then let's run this one now. No. There we go. I didn't save it. So as you can see, it's still calculating the sum of the cubes. And then you might in the background start to hear the fans on my computer go haywire, because I have them set for when the CPU gets hotter to, ramp up. So that, again, this is Grover with Blue Collar Codes, quick and dirty, going over how to time your functions using perf counter. And I'm going to end on the fact that, so calculating the sum of squares for 1,000 input value was 0.022 seconds, and you have a whopping 28 seconds when you go up to the cubic function. So if you could imagine what a factorial function would be, that would be quite outrageous. Hope you enjoyed this video. See you next time. Thanks for joining.